I might have forgot to unmute that earlier, so sorry to the Zoom class if I was talking at you and didn't remember to unmute. But it looks like we can start. Welcome back, everyone. So on the right column here, there's just some quick thoughts before we launch into the notes. Everything that you see on here is duplicated in the notes, and we're going to write in some of the thoughts as well. But the major announcement for today is our second exam is scheduled for next Monday. So early today, early in the morning, I sent out instructions to each person in the class individually on how to schedule your exam two. I sent it through the Canvas messaging system, so this little inbox right here. So you should see a message in your Canvas system, but also it should bounce to your ISU email address as well. So either way of accessing it, please try to get your exam two scheduled as soon as possible just to get it out of the way, avoid any weird issues with the testing centers. And if you don't see it or you have any questions, feel free to email me, contact me right away, and we'll get it sorted out. But that's the major announcement. This exam is only over these three sections. I was thinking of pushing 6.3 onto it, but I didn't want to make it feel kind of unbalanced where exam one was also over three sections. It's going to involve 4 questions altogether. One question in section 5.4, a question in section 6.1 where I randomly am selecting either a sine or cosine, and then 2 questions from 6.2 where I'm going to randomly select either a tangent, cotangent, and then randomly selecting either a secant, cosecant. So it will be an equal smattering of the same kind of graphing exercises we've seen. Not every single problem because it's also a 50-minute exam like all the rest. The other thing that's new about this exam is you're welcome to bring a basic scientific calculator for use on this exam. All the questions are going to require exact answers in the end, but it can help out with some intermediate steps, in particular with section 5.4. Well, that's the major announcements for the day. Section 6.2, a lot of people have finished this one already. For the best thing to do to practice and prepare for the upcoming exam, get this squared away, and that's the last section on this list here. If some of these things have gone late, I do accept full credit on these because that's really, once again, probably the best way to prepare for the exam. Work through the homework exercises, and I'll try to get your feedback sent to you as soon as possible. If you're all caught up on homework, then take a look into the feedback when I email it back to you. And you can look into these additional documents for more exercises, the same kind of documents that you saw for exam one. Well, I think that's it for my announcements. Any questions or comments at the moment, folks, about exams, the prior or upcoming sections or otherwise? Okay, well, we're about to jump into the inverse functions. Oh, we got a chat first. Let me address that. The time limit will be 50 minutes on this exam. And same for the third exam as well. The final exam will have a time limit of 2 hours altogether. Absolutely. Thanks for asking about that. Other questions so far? Okay. Well, we're going to jump into the inverse function section. And this is really just the major punchline when we say inverse functions. Doesn't matter if we're talking about the principal square root as it relates to x squared on a restricted domain, or if we're talking about the exponential function as it relates to its corresponding logarithm, or if we're talking about the sine function as it relates to the inverse sine function. Yeah, either way, no matter what the concept is or the type of function is, if the concept is inverse functions, all we're literally doing is swapping inputs to outputs. There's a little bit more to that story because we have to be extremely mindful of domain and range. That's where it gets a little bit tricky. And that's why we'll probably take about a day and a half at least on the section 6.3 notes. But this little idea of swapping inputs and outputs in this kind of way is, again, a great way to think about inverse functions. Then inverse functions are interesting the way we indicate them. We use this thing in the power spot to -1 to be our big way to indicate a function inverse because it's sometimes able to cause confusion, genuine confusion. Occasionally, you'll see it written this way. An inverse sine or inverse cosine or inverse tangent could be called an arc, sine, arc, cosine, arc, tangent. So this is a way to avoid any ambiguity, The only downside to it is it's clunky. Takes a long time to say it. But if you're practicing things in Desmos, that's the way you have to say it. You have to say arcsine. Other calculators do use sine inverse. And the next big warning, this is also in the notes, but we might as well look at it while it's on the page here, is that that power is specific where we put it. If we put it right here, we're talking about the inverse sine function. If we put it out here, and we really should put parentheses unless we mean x to the power of -1. So if there's a power out here, this is not the inverse function at all. This is just the multiplicative inverse of sine x. 1 over sine x is what it would look like. But that's just a different way of saying cosecant x. And cosecant x and sine inverse x are totally different functions. They have completely different domains, different purposes. And so that's another thing to keep in mind. The notation is subtle. Where you put that power to indicate an inverse function means you're really looking at inverse versus you're looking at cosecant down here. So those are the warm-up topics so far. Any questions before we actually jump into the notes? Okay, so going into the weekend, this is where we left off. A big wall of technical text, definitions, theorems, tests. But the main point was, if we want to find an inverse to the sine function, we graph the sine function, here it is, but only on a very, very specific domain, just from -π/2 to +π/2. That was the domain where the sine function is 1-to-1. And if it's 1-to-1, that means the function was invertible. So this domain from -π/2 to +π/2 is the maximum domain we can find, the maximum in terms of length, for which we can inverse the sine function. And when we go to inverse it, this theorem just tells us the graph is going to be symmetric about the line y equals x. So the 45-degree line going through the origin like that. The black line is the inverse function, and we do see that nice reflection across the 45-degree line. So when you look at the domain and range of sine, because we're just swapping inputs and outputs like we discussed earlier, you literally also swap the domains and the ranges of both functions. So now sine inverse has domain -1 to +1, range -π/2 to +π/2. And this feels like one of those things that we just mentioned and that we kind of take for granted down the line. But actually, these are really finicky. Being uncareful with domains and ranges makes these really foggy and difficult topics. So we'll make a big deal out of them as we go to compute down the line on the notes. So that's what we looked at right before going on to the weekend. Kind of a heavy topic, sorry about that. And we need to do this as well for the cosine function and the tangent function. The same trick is going to work for cosecant, secant, cotangent, but the use of those functions is kind of minimal when it comes to calculus engineering topics. So in this trigonometry course, we're just going to invert 3 of them: sine, cosine, and tangent. Here's what it looks like. Now, here's more information. First, it's a table. So if you want just a quick view of really densely summarized information, here it is. In its long form, here is another table giving us all the information we need to know about inverting sine, cosine, and tangent. None of these functions are fully invertible on their entire domain. So that's why it's called the restricted sine function, restricted cosine function, restricted tangent function. So we've shrunk the domains down. And when we go to look at these restricted functions, these are those restricted domains. Also printed down on the very bottom of this graphic. The range of both sine and cosine are -1s, +1s. But notice the domains are different, so we have to be very, very mindful of that. Cosine, if we want to pass the horizontal line test, we start at 0, and then we end right here at pi. You cannot go any distance to the right of that because the curve on cosine turns up. The moment Word lets me plot, there we go. If you go beyond pi, cosine moves up and it fails the horizontal line test immediately. And he couldn't go to the left because of, well, same problem. Fails a horizontal line test there. Tangent is not too big of a nuisance because if we go from -π/2 to +π/2, that's 1 full period. And that's kind of nice. This does pass the horizontal line test. So down below are all the inverses. Notice the swapping of domain and range on every single one of these. Domain becomes a range here. Domain of the inverse is the range of the original function. Then again, we have another swap. And this is where the swap becomes really interesting. Recall, that's a vertical asymptote, so the curve goes down forever, nonstop. So that's why the range goes from negative infinity as well as up to positive infinity, since on this end, the curve is going upwards without stopping as well. There's no upper value here. There's no lower value here. It's an unbounded function. So that means the range of our restricted tangent functions from negative infinity to infinity. And that means so is the domain. This is the only domain that's in the entire real number line. The other two are highly restricted, very small domains. Here, the domain is from negative pi over 2 to positive pi over 2. And that means it has a range going from negative pi over 2 to positive pi over 2 as well. That's a lot of arrows, but another thought you could keep in mind is if there is a vertical asymptote here, right at negative pi over 2, there should be a horizontal asymptote here at positive pi over 2, and that's in fact the case. Vertical asymptote here, the equation would be literally x equals positive pi over 2. We're always swapping x with y, and vertical asymptote becomes a horizontal asymptote. Y equals positive pi over 2. Let me write this as a y equals and an x equals as well. Missed my negative sign. There it is. That's really hard to read, actually. So the vertical asymptotes swapped into horizontal asymptotes. Domains and ranges swap as well. It's a lot of information to take a look at, but it's a good place to come back and stare one at a time to see how sine works, cosine works, and tangent works. That's one of the reasons I like this table right here. It tells us everything if we're just specifically thinking, what are domains and ranges? So our job is really just practice doing some computations. This is very much like sections 5.2, 5.3, where we're just evaluating the inverse functions at various inputs. I'll focus on one at a time so we can see what the features are with the domains and ranges for the restricted function and the inverse function, what kind of problems that we encounter, because it is finicky, like we mentioned. Well, any questions, folks, staring at this kind of wall of information? Okay, down below is just a couple things that we mentioned on the Canvas page. Instead of writing sine inverse, we'll often or occasionally write arc cosine. Let me try again. Instead of sine inverse, we'll occasionally write arc sine. Instead of cosine inverse, occasionally we'll write arc cosine. And likewise, for tangent inverse, occasionally, just so our eyes are used to seeing it, we'll write arc tangent. That'll be similar in the homework as well as when it comes up again on exam 3. Here's the warning again. Sine inverse this way is not the same as sine inverse this way. The position you put that power absolutely does matter. Sine inverse put in this position is just the cosecant function. And it seems odd because if it was power 2, these two have the same meaning. That's just because this is not a true exponent. It's just a way to say we're putting in an inverse function. So at this point, this is pretty much our job for the next about a day and a half, just practicing doing evaluations. Like I mentioned, we're going to do these one at a time. So for the moment, we're just focusing on sine, restricted function, and then sine inverse. So we're just on this part of the table, in other words. Our job is to do as many evaluations as we can before time runs out, and then we'll come back to it when we're on Wednesday's class. But a good analogy like we had on the Canvas page really helps out because this does feel like a new landscape at first, and it's much similar to when you first studied logarithms. For example, back in the day, you would have been faced with the problem, what is log base 2 of 8? If you're rusty on logarithms, I totally get it. It's easy to get a little bit rusty on these. Anyone happen to know the answer to that one? Oh, we've got a candidate. Absolutely. Good call, Kai. The value there is 3. That was meant to be a question mark, by the way, if you were wondering. If you weren't sure, here's the thought. Whatever you put here, you go like this. 2 to the power of the unknown needs to come out as an 8. So this is the thing that we mentioned on the Canvas webpage. There is a literal swap of input and output. Kai possibly just knew that a logarithm is the power that you raise the base to in order to get 8, or Kai is possibly thinking in terms of this swap. Whatever you put here and here, because it was 8, we have to also maintain this correspondence. But now in the exponential form of the equation, we know 2 to the power 3 is 8, and so that gives us the value of the logarithm. We'll do the same exact thing as we go to solve these down below. Really, this is a tool that gives us a nice check. That's how we're going to often use it. And we have other tools. If we're thinking in terms of what did we do in section 5.2, 5.3, well, we were defining trigonometric functions, and we took heavy advantage of the geometry of those trigonometric functions. So we're going to revisit that kind of work as well. So first one, sine inverse of negative root 3 over 2. Here's how I would probably start off each and every one of these problems. Go back to the good old unit circle diagram. Here it is. On this unit circle diagram, we have to be mindful of this isn't your ordinary sine function anymore. We have to restrict the domain from negative pi over 2. I'll put a little hard circle there to say that this is one position we can take. Here's positive down to negative. So we can take everything on this band from here to here as being in the domain of this function. That means everything out is forbidden territory. We can't use anything out here. I'll kind of convey that by putting in this kind of blacked out lines here to say any output that you give, like say pi, that doesn't work for this. Any output to sine inverse has range from negative pi over 2 to positive pi over 2. So in other words, the answers are all right here somewhere. We just have to find it. Here's the next thought we could have. Negative root 3 over 2, leaning on some of the skills that we used before, whatever the sine value is, it's a value on the y-axis. We're swapping input to outputs. So this is the input to the sine function, a value on the y-axis still, and that would be about here. Maybe slightly higher. It's about 0.9 if we were to round it. Oh, Control Z went a little too wild. Let me put that back. So it'd be about here. Then we can reverse engineer and say, what was the angle here? This is why plotting those angles and knowing where they're at becomes so valuable, because if you're staring at this and saying, that's pi over 3, good on you. Still, it's a good idea to just write down a unit circle every now and then and do a drill, put down all the angles like we mentioned from sections 5.1, 5.2, just to get a feel for where all these are. But that's the answer to this one. This one gives us an output of pi over 3. Let me swap my color here. And the really fast check is, you don't have to put your check on your exercises, but it can't hurt for the notes. We can say that we know this is true because sine, or hang on, I missed one thing. There's a negative sign there, isn't there? So if I check out sine pi over 3, I get root 3 over 2, and my check fails. Well, it's good to do the check, right? We're trying to aim for negative root 3 over 2. I wish I could say that was for the sake of just a good educational way to see how a check can be helpful, but that was a bona fide mistake. Let's reverse engineer this and find a different angle. Root 3 over 2 is about 0.9, but we're going to negative 0.9 way down here on that position. Now reverse engineer, go to find some angle in that position. I'll leave this one up to the class. Anyone happen to know what this angle must be? There's like infinitely many choices, but only one will work. Dennis says 5 pi over 3. That's a good call on that one, except this is where this gets finicky. The range right here tells us all the values that we can take, and 5 pi over 3 is out of range. It's the right thought. The angle here is 5 pi over 3, but it's not the output to this function up here. Again, that's where it gets really kind of tricky. Does anyone know another coterminal angle that's the same as 5 pi over 3? Yeah, go ahead. Yeah, absolutely. From class, you could use negative pi over 3. It terminates in the same exact position. And the good thing about negative pi over 3, it is in range right here from negative pi over 2 to positive pi over 2. Again, really finicky, right? Sure, we're swapping inputs and outputs, but we have to also at the same time pay very close attention to domains and range. Yeah.
Is there a reason you can't use 5 pi over 3 because you're going over that out of bounds zone?
Exactly. From the 0 here, 0 rotation, we can only go in the clockwise direction as far as negative pi over 2. From the 0 position, we can only go as far in the counterclockwise direction as positive pi over 2. Anything beyond is out of range, just like you said. So that's really tricky about these kinds of things. Let's put in here the correction, pi over 3, excuse me, negative pi over 3, struggling with negatives today. I'm not sure if you've noticed. So negative pi over 3. Now down here in our check, sign at negative pi over 3 is indeed negative root 3 over 2. And so we do have the swap that we're seeing. The outputs and inputs have swapped this way and this way. So one down, we have several more to go. And this is pretty much what our work is going to look like in this section, just practicing doing these evaluations. Any questions at all, folks, getting through our very first one? Okay, let's try it all out again. Instead of saying sine inverse in this way, we're writing out arcsine, but it's referring to the same exact function. The input here is 0 this time. That means you go to 0 on the x-axis, you'd be right here. The angle, if we were to repeat the same exact thing as before, would look like this. Just comes out. And that's the zero radian rotation. So based off this diagram, my conclusion would be that arcsine of 0 is 0. Then our really fast check would be sine at 0. We do know that to be 0. It's the x-coordinate, or excuse me, the y-coordinate for sine right at this position. And so, yeah, inputs and outputs have swapped. They're all zeros, so imagine they swapped, even though it looked all identical. So that tells us arcsine of 0 is 0 itself. Then pretty much same idea on every one of these. This is a 1/2, but because it said sine, we would go to 1/2 on the vertical axis right here. Then we have to find the right angle that takes us to 1/2, being mindful that we're between negative pi over 2 to positive pi over 2. That's the tricky part of all this. Going to the right until we hit the unit circle, the angle that jumps out to me from this graph would be pi over 6. And that would say, therefore, sine inverse of 1/2 is just pi over 6. The check now is take sine pi over 6. Here, sine at pi over 6, well, we're just going backwards now. It's the y-coordinate, and that's visually at 1/2, and in fact, it's exactly 1/2. So said in slightly different ways, sine inverse is taking all of your angles that used to be inputs and turning them into outputs in this kind of way. So sine inverse at a number is the angle that results in whatever that number was. If it's sine, we're talking about a number on the y-axis. If it was cosine inverse, we'd have been talking about a number on the horizontal axis. So same kind of idea as before. I seem to have lost some dots on these, but I don't think that's super necessary. Let's try out a couple more just to get a feel for this. And let me carry this table down in case we need to refer to it. Now, if we do sine inverse of -1. Well, at -1, we would be right down here, right where -pi/2 is in purple or whatever color that happens to be. That would tell us that this comes out as -pi/2. Right over here at -pi/2, the y coordinate is -1, since this is the unit circle. So it tells us as well that, well, if we evaluated sine at -pi/2, we would get a -1. And so that's matching our expectations so far. Well, that's a couple nice evaluations. The cool thing about it is, again, this is literally section 5.2 in reverse. Aside from the fact we're being extremely picky with our domain and range, because sine inverse itself can't give us certain values. Here's where it gets a little bit new in a certain sense. Here's some more summary information about inverse functions from way back in the day, pre-calculus 1. There's good reasons we like inverse functions. They assist us in equation solving. They cause a type of cancellation to happen. So if we put down some formulas here on the right to help us with part E, they go like this. F at F inverse of X. Whatever F inverse has done, F unwinds it, and it's just equal to X. That's not the whole story, though, because this right here has to be defined in the very first place. And so this is for all X in the domain of F inverse. So if we're in the domain in the first place, this is a great formula. And the reverses as well. F inverse of F at X is also X. So the thought here is whatever F has done to the input X, F inverse unwinds it, and we get X just right back. But this one is specific as well. This is for all X in the domain of F. And our domains, even if it doesn't say it explicitly, in the context of sine inverse, cosine inverse, and tangent inverse coming up, some of our domains, well, all of them are highly, highly restrictive. So this could fail in both directions. So the way we check this one out is take a look at the 1/5. It's going inside a sine inverse, and that domain is from -1 to +1. We are within domain, and so it tells us this one's not a big problem. There's a cancellation, and the whole answer is 1/5. We didn't have to do anything at all with that one. We just had to observe we are in domain. Lots of ways this could go wrong, however, so let's put down a second version. This one wasn't in the notes, but suppose it went like this. Sine of arc sine, or sine inverse, of 5. Now we have a really big problem. If a 5 goes in there, that's a strange looking 5. If we have a 5 here, arc sine at 5 is just totally undefined. We are way out of domain. Doesn't matter what else is in the problem whatsoever. There's no cancellation here. We just say undefined. So this part right here, for all X in the domain of F inverse, is critical whenever we use these cancellation properties. And likewise right here, for all X in the domain of the restricted function F at the same time. So any questions at all, folks, about dealing with these kind of cancellation properties with the inverse functions? Okay, here's a really weird one then. Kind of fun in a way. It's always interesting to see how weird this stuff can get. And this one, I think it gets the award. Let's take a look at how we might think about this. 7π/6, just like at the first problem where 5π/6 was out of range, this is not your normal sine function anymore. If we're going to use a cancellation law, that's what it would look like. Sine, the inverse is in front. A cancellation insists that that X is in the domain of the original function, and that domain is restrictive from -π/2 to +π/2. However, this one is defined. This one has an answer. We can't say undefined on this. We could lose credit. Here's how I would probably think about this. There's two ways. If you're an order of operations fan, that's probably the best way to think about this. We know how to calculate sine 7 pi over 6. 7 pi over 6, well, that one terminates in quadrant 3. It's just a negative 1/2. So this is sine inverse of negative 1/2. Just because this is new, we might draw in a new unit circle. Here's the restricted zones, and we can only go from negative pi over 2 up to positive pi over 2. I don't know why my graphics keep moving up and down, but I'll just do my best I can with that. Negative 1/2 is right here. Now we need a specific angle that's going to terminate right here. The angle that does that is, well, you could say 11 pi over 6, but again, that's a problem with sine inverse. 11 pi over 6 is out of range. So the next best thing is negative pi over 6. Negative pi over 6 is within this range right here. So the whole thing would be negative pi over 6. So that's one way to try to reason through these kind of problems. Work inside first, get a number out. This is absolutely defined. And we would get, hang on, negative pi over 6 was the thought I was trying to put down. We would get negative pi over 6 as the result on that one. Or here's another way. If you like thinking in terms of these geometric kind of drawings, 7 pi over 6 is right over here. Notice it's in the void region. This is out of range out here. But all you had to do is reflect this entire thing about the y-axis, and you land right on the negative pi over 6, the correct answer. So you could have taken this whole thing and just jumped over to negative pi over 6. But the big takeaway is cancellation doesn't work on this one whatsoever because 7 pi over 6 is not in domain of the restricted sine function. If it looked like this instead, sine inverse, and let's put something that's actually in the right domain. Let's put in maybe sine pi over 3. This one's no bother because pi over 3 is way up here, and the cancellation laws would work on this one. Sine inverse cancels with sine because the x this time is in that right domain, and we would just get pi over 3. It only comes out as something different whenever we are outside of this domain. I notice there's really two versions now. There's the version where it's sine of the inverse function arcsine. This one has its own pattern of attack. And there's a whole nother version when the inverse function's to the left and sine is on the inside. We'll study these again when it comes up with cosine and tangent problems as well. But that's our quick rundown of the various things that happen with the sine and inverse sine. Any questions at all, folks, navigating these ones? Okay, lots of little tiny things to think about. That's why section 6.3 is one of those sections that tends to come with lots of review material. So if all this seems kind of wacky in a way, reviews the inverse functions either on the video. The document here has some applications at the end. The assignment 6.3 also points you to some helpful reading. You can read some examples out of the book while working with inverse functions. And all that material really helps tie all this together. At the end of the day, we are swapping inputs and outputs just like this. We're paying extremely close attention to domain and range to make sure everything falls in the right place. So let's try that out again. New land, we're now dealing with cosine functions, and cosine functions go differently. Notice for cosine, the domain of our restricted cosine function is 0 to pi. The range is the same, negative pi over 1 to positive pi over 1. But that domain causes a few issues. It means the answers to cosine inverse, they're all in the range. Any answer you put down on paper to any one of these has to be specifically between 0 and pi. We can start off though, just like before, we can begin by just putting down big unit circle diagram. There it is. Probably the nicest circle for the semester. Keep saying that, but this one looks pretty good. A little lopsided, a little vertically stretched, but not too bad freehand. Here's our whole unit circle, and from 0 to pi means we're starting here, the 0 radian measurement. We're ending here, just half the period of cosine, just like with sine, but we're in this range now. So any output we give to any one of these functions has to fall in this region. In a certain sense, cosine, I think, is a little bit less tricky because sine had the negatives with the positives at the same time. We'll see that again with the tangent. Cosine is just a little bit unusual. It's an odd one out on that. It also conveys anything here is in a void region. These are all out of range. Or if you're thinking in terms of domain, they're out of domain for the cosine function here. Aside from all of that organization, the work looks exactly the same. We look into what function are we evaluating on. If it's a cosine function, we're plotting something on this time the x-axis. We're going to be more mindful of the negative sign. This one's at negative root 3 over 2, so this one's very similar to part A of the last example, except it's a cosine. So we put negative root 3 over 2 here. There it is. We need to discover what the angle measurement is right here. Whatever you say that angle measurement is, that should be our answer for cosine inverse. Anyone recall what that rotation should be in radians? Put a question on it while we're meditating on it.
Maybe 5 pi over 6.
Yeah, absolutely. Thanks, Andrew. I think I heard it whispered as well in class, but I wasn't too sure. So 5 pi over 6 would go up here. And that means we did it, folks. Cosine inverse is 5 pi over 6. Oh, and I just saw the chat come through. Close. The 2 pi over 3 would have been the one that goes like this, closer to the y-axis. Well, again, these are kind of tricky in a certain sense. We need to know where all of our angles are really to get a good read on what the outputs are for these. So that's why I would encourage you to, as you go through section 6.3, maybe before you're doing the homework exercises, maybe before you're reviewing this for exam 3, go all the way back, and I know this is quite a ways back, to I think section 5.2. Let me see how accurate my memory is on that. In section 5.2, at the very end of this document, no, my memory wasn't very good. Go all the way back to section 5.1. So the first section of the semester, this computer's working really hard. Adobe seems to be overloaded with a bunch of strange, unnecessary things these days. It's not as lightweight as I remember. But go all the way back to section 5.1, build a big unit circle like this, and place all those angles like you see them here. Maybe not so much the 5 pi, 3 pi, or the, well, maybe not the 4 pi, but 2 pi is pretty good on there. If you can just reverse engineer, put this down, just as a quick drill exercise before doing these problems, it helps tremendously because we need to find out where all these angles are going to end up anytime we're dealing with these inverse functions. So it was useful for sections 5.2, 5.3. It's just as useful in section 6.3. But in a way, that's kind of cool. It just means we're reviewing it a second time over. Like before, there's always an available check for us. If this is accurate as we put down on paper, 5 pi over 6, then calculate cosine 5 pi over 6. We would rotate to 5 pi over 6, grab the x-coordinate, that's pretty close to -1, so it would in fact be negative root 3 over 2. That means we did it, folks. That's one down. And on to the next ones. Well, next is arc cosine at 1. We're talking 1. That means we are right over here. on that specific spot on the horizontal axis, that means the angle that takes us there is the 0 radian measurement. So the output to this one is automatically 0. Quick check, cosine of 0 is in fact 1, and so that's a really fast check on that one as well. And just to summarize what we've seen so far, sine inverse of 0 comes out as 0 because sine 0 is 0. Cosine inverse at 0 is 1 because cosine at 0 is 1. Or hang on, I got that mixed up. Cosine at 0 should go like this way. Cosine at 0 is 1, so cosine inverse at 1 is 0. Sorry, I got my thoughts mixed up. It's nice that they interchange, but I think I did too many interchanges. So another one similar as before, cosine inverse or arc cosine at -1 would place a value at -1 way over here. I think I meant that for that to be green. So here's -1. That would take us to this radian measurement, giving us the pi. And we know from experience, cosine pi equals -1. The checks are all in orange just to convey it's optional. I can imagine that's something that you might do on your mental blackboard or maybe on scratch paper. If you put it on your homework as well, a check couldn't hurt. But if all you gave me was arc cosine -1 is pi, that's pretty much all we're going for on these. Pretty fast problems, but they have a way of being tricky, so we're going to be careful with them as we go. So far, nothing too crazy with the next one. Cosine inverse of 1/2, which means go to 1/2 on the x-axis. We're right at that position. Then, sorry, getting my color coding mixed up. I think I wanted these to be blue after all. And so go to 1/2 here on the x-axis. We move up to find the angle here, and this one is just ordinary pi over 3. So that tells us cosine inverse of 1/2 is pi over 3. Quick check on that is, it's also true, cosine at pi over 3 equals 1/2. We're literally just reversing the process how we would have calculated this in section 5.2. We would have placed pi over 3 here, go down to this position on the x-axis, which is 1/2, and we would have read out that value. Here, just a complete reversal of those instructions gave us pi over 3 for cosine inverse 1/2. And let me copy this table down so we can reference it for the next ones. Next one is cosine inverse 5 pi over 6. From the last problem, we know we have to be pretty careful with that. Let me redraw this. For cosine, we need to use this information here. The domain goes from 0 to pi, so we're in the 0 to pi range if we're thinking cosine inverse. That means everything out here is totally restricted. But 5 pi over 6, as we looked at it before, it's not too bad. Here's 5 pi over 6. It's in the domain of the cosine function. It's in the range of the cosine inverse function. So cosine inverse with cosine, this one uses a cancellation law for inverse functions. We can cleanly just cancel those out, right? And the output is just 5 pi over 6. If it said 7 pi over 6, then that would have been the trickier problem. But any questions at all, folks, getting through part E? Okay, here's a challenge question with domains and ranges. Anyone see the best answer to part F? Cosine of arc cosine at 3. Good call, Kai. This one is just totally undefined. In a way, that's kind of nice, right? There's nothing to do on this one. But let's fill in the dots on why that's the case. Thinking in terms of order of operations, well, if you try to calculate arc cosine, what would you do? You would have to determine first are you in the domain of arc cosine? But that domain is from just negative pi over, excuse me, -1 to +1. Well, my control Z is taking things off backwards. Let me try that again. Here's the domain. 3 is exceeding the upper limit of the domain. The maximum value you can put here is just a +1. So this, just as it stands on paper, is undefined. No cancellation law whatsoever on this one because cosine inverse or arc cosine of 3 didn't have any meaning in the very first place. And that's exactly what we were doing up here. Before we even attempted the cancellation law, we observed, because the inner function is cosine, that 5 pi over 6 is in domain. Once it was in domain, we celebrated and we just canceled and got the output 5 pi over 6. So good call on those. These are really pretty tricky. It's all about getting the domains and ranges down just right. So this is a good table again to have at the available as you're doing your homework exercises. Lots of things that can come up are things like, say, this one down below, cosine inverse cosine 2.7163, or arc cosine negative pi over 4. So let's work through these next tricky ones and see what we can get out. Let's see, I don't want to rush to the last minute as well. Maybe part G will be the last one for the day. Let's see how this one should go. We're doing arc cosine of cosine pi over negative pi over 4. Well, thinking in terms of the domain of this cosine, we are out of domain. It's only positive values or 0. There's no negatives whatsoever in that domain. But when cosine is the inner function, it doesn't automatically give you an undefined. That's the next weird thing about these things. This has an answer. Oop, didn't mean to throw my mouse at you. The first thing you'd want to do is just work in terms of order of operations. I think that's the cleanest way to see this one. So here's the unit circle diagram once again for the cosine inverse situation. The angle negative pi over 4 is an inconvenient one for us because we're in this void region, negative pi over 4. But remember what we did before that this occurred. We did a kind of reflection. It was about the y-axis. And let's see if we can compare how the reflection will happen on this one. So first thing I'm going to do is just calculate cosine at negative pi over 4. This turns into arc cosine. This whole thing on the inside is going to turn into negative pi over 4. We're up here, positive root 2 over 2. So we're now doing arc cosine at positive root 2 over 2, following order of operations. That parenthesis just looks a little funny. Root 2 over 2 is approximately about 0.7-ish. Because this is a cosine inverse, we're going to go to 0.7 on the x-axis, taking us here. And now we just have to find the right angle. Negative pi over 4 didn't work, so we go up instead. Notice that before, when this situation occurred, we reflected about the y-axis. This time, we're reflecting about the x-axis and picking out positive pi over 4. So the answer to this one is just pi over 4 itself. And other interesting things we're going to take a look into on the next one. You know, we could do this one in a minute, but let's not rush that one. The answer is 2.7163, but we'll discuss the reasons why. See what happened when we come with all the rest of these when we come back on Wednesday's class. This stuff is pretty finicky, like I mentioned, so if anything just seems weird when you try these out, you know, bad thing you might do is put it in the calculator, see how close your answer comes. If the cancellation law doesn't work, it's because something up here causing a problem with domains and ranges. But any last questions at all, folks, before we call tonight?
Yes.
Yeah, go ahead.
So the role of related ranges going to be on future tests.
That's a great question. On the exams, the math department itself has a policy for this particular class, trigonometry, and their policy says, that's the wrong thing. Their policy says that I'm not to allow any notes except for on the final exam. I can put a formula sheet at my discretion. So I can't allow formula sheets or anything, formulas or sheets or anything like that on our exam. But when I really look at this table, it doesn't feel like a formula, right? I've actually allowed the one part of the unit circle on exam one, right over here. I felt like, this wasn't really a formula. It's just some geometric information. I'm going to do that on exam two, exam three, the final exam. And so I feel like this is in the same spirit. I'm not giving you formulas. I feel like I'm not violating the math department policy. So yeah, I think I would put that on the third exam. This is technical enough that having access to that information is just about what anyone would want when they're working with these kind of functions. If the math department disagrees, well, I've been chewed out before. We'll fix it next semester, but that's what we'll do for this semester.
Yeah.
Other questions at the moment? Okay, well, have a great night, folks. On Wednesday's class, we'll just return to this material here. Thanks, folks. See you Wednesday. Another day down. There's like 30 classes, so that's one out of the set.
Glad you pushed the due date for 6.2.
Yeah, I've been forgetting to do that. I should have done that after class last Wednesday. Sorry about that. Yeah, because we finished it a week ago on Wednesday. Yeah, I tried to make sure that's not going to happen with 6.3. I went aggressive on it already. I didn't even attempt to think we're going to finish it on the 13th. I'll try to keep those due dates more in line with what we said we're going to do and not push them like right after the weekend ends.
Certainly. Because of the 3 different assignments too, we got like 2 of them, I haven't even touched 6.3 yet,
Gotcha, yeah.
so,
College sometimes gets pretty busy, doesn't it?
yeah. Especially when one of your classes forgets to give you your book.
Ouch. Yeah, that's pretty rough.
I still would like to do the nail over that since, beginning of the semester. Still trying to recover from that, not letting it slip over right away. So,
In which class?
it's not your class, it's a different one.
Yeah,
It was the geography class or something.
gotcha. Yeah, that is pretty dang rough. Yeah, if you don't have access to your course materials and then they're just pushing through the course content, it feels like you're just watching yourself get behind week after week. Yeah, that would be tough. Dang. Was that like a book bundle issue or something else?
I think that was a book too.
That's happened before in one of my classes in statistics where everyone had their book for a while. This was a Pearson product for statistics. And then like right around now, right around midterm, anyone that opted out of the book bundle had their course materials yanked. And it took like 3 or 4 weeks for people to get it back. So that's 3 or 4 weeks of the semester. In the middle of the semester, they didn't have their book. That was the weirdest thing ever.